Good day to everyone. So class, today I will start our lecture with gas management system in gas chromatography. So class, when you are thinking of installing a gas chromatography, you need to consider the entire system in order to run the new chromatograph at highest efficiency. Choices to be made with carrier gas selection and how that selection will influence your chromatography you have to be considered. So the detectors that you will use will dictate your first choice of gases and later other factors that define in your analysis method, which will finalize the carrier gas selection process. So basically class, in gas chromatography, carrier gas will be the mobile phase. Fuel gas is for the flame or ignition. Markup gas is introduced into the detector or cell to sweep the cell more rapidly and reduce the peak broadening. So based on the figure here, you can refer to the given figure here, class. So the markup gas, hydrogen and air, okay, into the column, it will flow into the column flow. Okay, the rate will be 1 to 10 ml per minute. Okay, so I will explain this further, okay, in upcoming slides. Okay class, now these are the gases that used with commonly for the common detectors. For example, ECD. Okay, the carrier gas will be nitrogen, argon, okay, 5% methane. Okay, another type of ECD, they do have a helium carrier gas. Okay, as for the FID, the carrier gas will be helium, hydrogen, or nitrogen as well. So as for the fuel gas, air and hydrogen, markup gas usually nitrogen, helium, or hydrogen, or same as the carrier gas. So this will be the common gases that used, okay, in the commonly used detectors. So now class, the gas requirement of gas chromatography system with flame type detectors. For example, class, if you can refer to this table, okay, basically dual pack column gas chromatography with two detectors, okay, the carrier gas, okay, air, which is for the fuel, and hydrogen, okay, gas, the flow rate and the total rate, okay, it's given here. As for the dual capillary gas chromatography, okay, usually the markup gas, okay, there will be another one which is the markup gas. Okay, so markup gas usually, often but not always, and it will be usually the same as the carrier gas as well. Okay, so as for the uh, A is actually other detectors may not require fuel gas. For example, like this type of detector, they don't require fuel gas. Okay, so usually the dual capillary gas chromatography system, they do require markup gas class. Okay, so now, so choice of carrier gas. Okay, we can explain the choice of carrier gas by using the Van Dimter plots. So basically here class, the minimum value of HETP is not only the consideration, okay, in order to choose the carrier gas. When we want to consider the best carrier gas for our analysis, we have to consider more than the minimum HETP number. Okay, according to our previous lecture, okay, as our HETP number lower, our efficiency of, our column efficiency will be good, and basically our separation will be good. But here, when we want to choose the right carrier gas class, okay, the minimum HETP number according to Van Dimter plots, it's not sufficient enough. We have to consider other factors as well. Okay, of course, the minimum HETP number is important, but we do need to consider other factors as well in order to choose the right carrier gas for that particular detector. So class here, according to this figure, okay, basically you can refer, okay, the plots for the hydrogen, helium and nitrogen. Okay, so basically class, you should pick a carrier gas that has a slope, okay, that shows the least reduction in HETP number as the linear gas rate increase. Okay, and this will gives you the greatest flexibility in the ranges of flows without the loss in efficiency. So basically class, here hydrogen's HETP, here hydrogen's HETP's optimum starts at flow at least 4 times higher than nitrogen and so thus it provides the shortest analysis time or the fastest run time when we run at its optimum or higher linear gas rate. So hydrogen usually become the gas of choice with very long column where our runtime reduction, okay, is paramount. So class, another factor is actually safety and cost of carrier gas also plays an important role, okay, in the carrier gas selection. So our main concern for safety, it deals with the fact that column do breaks in ovens class, column do breaks in oven. So most of the analysts, okay, are concerned with using hydrogen as a mobile phase because of this fact. Okay, so in the most countries they use helium, okay, because it's inexpensive and it readily available in high purity. So for this reason, the most common choice of carrier gas will be helium. Okay, so the viscosity of the mobile phase will change as you increase the oven temperature. So class, basically the effect of temperature on viscosity of four common carrier gas, okay, given here. So the viscosity of the mobile phase will change, okay, according to the oven temperature. If you can refer to this table, okay, basically it's in a increasing amount. So basically the viscosity effects, okay, causing possible problem during the temperature programming as well. So basically class, several gas chromatography detectors, they are very sensitive to the change of the flow rate that will result in the mobile phase viscosity, okay, changing in mobile phase viscosity. So the obvious results of these effects is the displacement of your baseline during the temperature programming. So and another factor that is responsible of the detector is affected by the flow changes because of the temperature's effects on viscosity. So class, to avoid this problem, we should look for a gas with smallest ratio of viscosity to diffusion coefficient. Usually class, nowadays the modern gas chromatography system, they do compensate all these effects by the use of back pressure regulation, which is combined with the flow control, that is computer control. Basically it's to adjust the viscosity change of the carrier gas with temperature change. Okay, so let's move on to the gas impurities class. So in general, chromatographers, they do agree that oxygen, water, oil, okay, for example hydrocarbons, carbon monoxide, carbon dioxide, halogens in gases supplied to chromatograph can cause baseline disturbance. It can basically disturb the column or damage the detectors. So class, here according to the given table here, the acceptable purity levels for chromatography grade gases is actually for the helium, nitrogen, air, hydrogen, argon, okay, or methane. So all the limits are given here in ppm. So you can also you may refer to this table. Okay, basically overall generally is less than 1 ppm. Okay, it should be fine. Okay, the gas impurities and minimum purity levels for chromatography grade gases usually class 99.9995. Okay, when we buy all these, we should make sure that the percentage is actually 999.9. So gases for a detector support, usually air which is dry, it should be 0 grade or better. Hydrogen should be 99.9995. Okay, so class, now As for the gas impurities, for example, water, carbon dioxide, carbon monoxide, and oxygen, actually they can damage the column by reacting with the stationary phase. Actually, column can be constantly damaged at the temperature higher than 140 degrees Celsius. So the injection of air onto the columns that very sensitive to oxygen can show immediate baseline disturbance and long-term column degradations. So similarly, class, reactions of oxygen, carbon monoxide, and carbon dioxide on detector also resulting in baseline disturbance, and with some special purpose detectors, which permanent damage to the detector also has been reported. So, for example, class, here, this column is exposed to 100 microlit of air. Okay, so the phase oxidation was monitored by observing the baseline as air which was injected into the column. So the full scale baseline deflection followed by the baseline instability reveals that the phase is severely damaged. So class, uh, you can also compare. Okay, this is the splinter vent open, and this is splinter vent open but the undamaged column. So basically the oxygen degrades the thin face of capillary column. Okay, because due to the column was exposed to 100 microlit of air. So here in this type of separation class, carbowax, okay, column was used. The oven temperature is 155 degrees Celsius. The carrier gas was helium, and the detector was FID with the splinter vent and septum perch turned off for 25 minutes. Okay, so this is the example of the chromatogram that you will get when the baseline was in, I mean, when the baseline was a bit disturbed, okay, due to some factors, something like some factors as we discussed. Okay, so now class, effect of rapid degradations of the capillary columns. So basically class, the capillary column will degrade. Okay, so that means class, here we are keep mentioning the degradations of the capillary column. That means the something that happens to the stationary phase. Okay, maybe the stationary phase become thinner, or the layer of the stationary phase leached out or something like that. Okay, so class, here the packing material is here, it's a phenol mixture. So the new column, after it was exposed to air leak, class, so the resolution basically lost. Okay, we can monitor the loss of resolution by the separation. Okay, if you can observe properly the given chromatogram. So before, okay, when the column was new, the separation was not to say very good, but still okay, class. Okay, there are some peaks is unresolved. Okay, but after 14 days of exposure, actually the separation was very bad. Okay, it's gradually decreasing. Okay, and after 28 days, the sensitivity of the column is even, okay, bad, and the resolution is lost. So that's why this one is actually the column is start to degrade, class. Okay, so now gas impurities. As for the hydrocarbons, so given figure shows the baseline disturbance caused by hydrocarbon impurities. Okay, zero packed, zero air, cylinder air, and the house air. So class, the house air is actually, they do can disturbs a lot, okay, during the separation. So these are the effects due to the gas impurities, okay, hydrocarbons. So now impure gas, carrier gas, can also cause the baseline instability on sensitive detectors. For example, class, like here the separation is actually quite bad. Okay, especially the peak number 2 is almost same as the noise peak. So this is due to the impure carrier gas, which can cause the baseline instability on sensitive detectors. Okay, so class, now let's move on to the GC for a qualitative and quantitative analysis. So class, now Qualitative analysis is actually the analysis in which the substance are identified or classified. Well, as for the quantitative analysis, the analysis in which the amount or concentration of the analyte is estimated or determined. Okay, and we have to express that in the numerical value in appropriate units. Okay, so qualitative analysis may take place without quantitative analysis, but quantitative analysis, it requires the identification first, which is the qualitative analysis of the analyte for the numerical estimation, okay, to be given then. Okay, so now class, qualitative analysis is based on mass spec. So the chromatography parameter used for a qualitative analysis is the retention parameter. Unfortunately, actually retention parameter also cannot conform the peak identity, and the GC are often to couple with MS to the okay, MS, and it will be to the GCMS for the qualitative analysis. Okay, you will learn mass spec in the mass spec lecture class in the mass spec course, okay, in upcoming semester. So these are the another one example of the qualitative analysis. So basically class, the parent molecule, okay, it will undergoes a reaction, and parent and the daughter. So we will compare the parent and the daughter, okay, by using the mass spec for the qualitative determination. So, and based on retention time class like GCFID, we are using retention time because we don't have the mass spec or library to compare with. So basically the retention time for the given solute can also be used for its identity. Okay, if the following column variables are kept constant. For example, the column length, stationary phase, and its thickness. Okay, when we are talking about the stationary phase thickness, actually the liquid loading class, and the temperature programming and carrier gas flow rate. Okay, all these variables should be constant so that we can use the retention time, and we will compare with the standard retention time for the qualitative analysis. Okay, so this procedure is not very effective if the number of possible compounds is large and the retention volumes are not are not specified. Okay, so it's actually a bit difficult to sometimes to identify those peaks by using the GCFID. That's why we need GCMS, okay, for further confirmation. So class, now selective detectors and dual detectors basically is used to identify classes of compounds. So it's use of two different detectors in parallel at the exit of a GC column, so called dual channel detection, where two signals are recorded simultaneously, which will produce the parallel chromatograms. Okay, so which is they use two detectors like electron capture detector and flame ionization detector. So it's like it can give further confirmation on our qualitative analysis. Okay, and offline instrument and test also can be done, class. Okay, one could also collect the effluent from the GC column, and we can also identify it, okay, with suitable instruments such as NMR, FTIR, and MS. Detectors must be non-destructive type, because class, if our detectors are destructive types, usually we can't get the sample. Okay, our sample will go into the waste bottle, and we can't use the sample anymore. If our detectors are non-destructive, so we can get the sample back. Okay, so something like that, class. Okay, now as for the qualitative analysis, class, online instrument, okay, GCFTIR also sensitive, okay, method of data handling is also contribute into the qualitative analysis. Okay, there are two common interference, okay, will be introduced in FTIR method, which is during the sample preparation for FTIR. It's due to the matrix isolation or light pipe. Okay, it's due to the light pipe. It's due to the column effluent is passed through the heated IR gas cell, which is the light pipe, and the matrix isolation is actually the effluent is condensed and frozen into a matrix suitable for analysis by IR. So basically, FTIR is non-destructive detector, and therefore it can be also further coupled with MS, so GCIR-MS, okay, something like that, class. Now, a typical chromatogram here, class, with the peak height, peak area. Okay, you can refer to this chromatogram. Basically, class, the quantitative analysis can also be performed on the comparison of either the height or area of an analyte peak, okay, which has one or more standards. So if GC conditions are controlled, both peak height and weight, peak height and area, okay, peak area and peak height will be proportional to the concentration of the analyte, okay, provided that all other parameters should be controlled. Okay, so the peak area is actually independent of the broadening effect, whereas the peak height is depending on the broadening effects. So broad peak is reduce the peak height. So with the peak measurements in hand, the next step, we can convert the size of the peak into the quantitative, we can convert the peak area, okay, the size of the peak into the quantitative measurements of the analyte. So basically here, class, the recommended way of the interpretations of the chromatogram is actually peak area. Okay, most of the people, they use peak area because peak height also can be done, but just that peak height sometimes it's very much dependent on the broadening effect. So if, let's say, if your peak is broad, then your peak height is also the broad peak usually will reduce the peak height. So that's why it's better to take the peak area rather than the peak height, okay, for the quantitative analysis. So this is actually old GC instrument class, so it will give like retention and how much the peak area and peak height, so that we can plot the calibration curves for the quantitative analysis. So class, usually the most common method that most of the analytical chemists use is the external standardization, where this method is usually performed graphically and may be introduced into the software of the data system as well. So the known amounts of the analyte of interest are chromatographed, and the area are measured, and the calibration curves is plotted. So basically, class, the important requirements here is sample, which is the unknown, or standard solution must be analyzed under the similar condition as the calibration curve standards. Okay, so to obtain the linear calibration plot, the column and detector has not be overloaded, should not be overloaded, and the electronics should respond linearly. That means, class, as the concentration increase, the instrument response should also increase. Okay, no apparent component adsorption in the injection port of the column, because we don't want any interference during the plot of calibration curve. So class, basically, when we want to analyze the sample, usually the requirement for the calibration curves and the sample should be the same. Like, the condition should be the same, so that we can use the sample, we can use the calibration curve to analyze the samples. So basically here, class, we will get the equation, okay, straight line equation, which is y equals to mx plus c. So by using that equation, basically we can calculate the concentration of the unknown samples. Okay, this is the external standard method. Okay, so one of the troubleshoot way for the external standardization is actually, ideally the peak size will double when the amount of injected analyte is double. If, let's say, the peak size is not quite double, so it may be due to the column may be overloaded, or the peak shape may be distorted, or the detector capacity may be exceeded. So where possible, so we should operate below this point, by using the smaller sample size or by diluting the samples. Usually class, we will do a very low concentration so that we don't overshoot, or we can't we don't, you know, go beyond the capacity of the instrument basically. Okay, so we have to make sure all that during the external standardization method. So class, here this figure shows the effect of sample size on retention time. Okay, column A, which is not overloaded, while column B is slightly overloaded class. So basically when it's slightly overloaded, actually we will take the value at this point. Okay, at this particular, for example, retention is 20 minutes, so we will take the peak area of 20 minutes. So here the A is not overloaded, is right. So of course class, we will follow the 20 minute for B. So but you know, the column sorry, the peak was a bit broad, so basically we will choose the lower value because the retention time was shifted, and C is even more worse. So in this case class, we won't get a linear calibration curve. Okay, we will get a negative calibration curve. So the response won't increase as the concentration increase. So this is due to the column overload. Okay, severe column overload class. As for the C, I will say this is a very severe column overload. Okay, so you have to make sure all these points have to taken into account when we are doing the calibration curve by using instrument. Okay, so second troubleshoot way is actually failure of the calibration curve to extraplot through the origin. So class, basically overlapping with the contaminants that could co-elude with the analyte of interest, and this can often be avoided by proper sample handling and proper choice of column and both materials of construction and packing. And it is possible to work with the calibration curve that does not pass through the origin, but it also requires that the calibration curves can be generated quite frequently. So usually class, we have to run the calibration curve before each run so that we can double confirm that our instrument is working properly. Okay, so that is one thing class. Okay class, now let's move on to the internal standardization. This way of quantitative analysis is a bit different, because here the standard is added to the sample in about the same concentration of the as the analyte of interest prior to the GC analysis, and this is actually particularly used for the technique that is not too reproducible and situations where it does not or cannot cannot be recalibrate often. So usually class, internal standard basically a pure compound added to the sample in a known concentration for the purpose of eliminating the need of measure the sample size in quantitative analysis and the corrections of the instruments variation. Basically the criteria should be, okay, it should elude near the peak of interest and must be resolved from them. Okay, it should be well resolved from them, and chemically should be similar to the analytes, do not react with any sample of component, and it must be available in high purity. So basically class, we will use the internal standard for the further verification. Okay, it's a kind of the validation method as well. Okay, using internal standard, which is, it shouldn't be same as the analyte that we are using, it should be different from the analyte that we are using. Okay, that is the internal standard we will use in the analysis for the validation. Okay class, here, okay, I've given some example of calculation, okay, for the internal standard, how the internal standard will be prepared class. So basically the calculation is given here, you can go through the calculation just for your knowledge class. Okay, now so let me move on to the standard addition calibration. Okay, basically an additional known quantity of the analyte is added directly to the samples following the initial analysis. So the concentration of the analyte in the sample can be determined by extraplot by extrapolating the calibration curve. The major advantage of this method is actually we can eliminate the matrix effects, and in chemical analysis, matrix refers to the components of the sample other than the analyte. So the matrix can have the considerable effects on the way the analysis is conducted and the quality of the results obtained, such as such effects are called as the matrix effects. So class,